If you ever noticed, for instance, that the sky is blue, and that's beautiful, you might have also noticed that bubbles are pretty awesome. So I've got this jar full of bubbles right here. Unfortunately, we also drilled some holes through this. So you can make bubbles by, how can you make bubbles? I guess putting some glycerin together. Look at this bubble right here. I'll make some bubbles. The cool thing about the bubbles is, whee, slurpy, slurpy. No, put some bubbles at the top, that's what I'm talking about. The cool thing about bubbles is they make awesome rainbow patterns. I don't know if you can see that on those bubbles. I'll try to get you a bigger one. But, there we go, wait for it. Bubbles, no bubbles. All right, just look at the rainbows in here. Ah, what a mess. Okay, see those beautiful rainbows? Now, we want to try to understand why those rainbow patterns are formed on bubbles. And if you're not seeing them on the video, go make your own bubbles. Have a little bit of fun. Sorry, this is such a mess. We'll see what we can do. Here's what I want to tell you. When a bubble, if we zoom in on it, we can try to understand why these things happen. When there's a bubble, there's a very thin film of soap and glycerin, I guess. And then I could have this light ray that's coming in from who knows where. And here's this light ray, and ray number 1, well, it's coming in here. This is the incoming ray. Ray number 1 is coming in, and the bubble material itself has a high index of refraction. So I'm just going to say n is greater than 1. Over here, we've got n is 1 because that's air on the outside of the bubble. And on the inside of the bubble, unless you're doing something interesting, n is also 1. So this is the surface of our bubble. A ray comes in and bounces off immediately. And I guess it bounces off at the angle that it came in at, right? Dotted line here, this angle is equal to that angle. Okay, great. But did it experience a phase shift or not? Well, it looks like it's hitting a fixed surface because this is a higher index of refraction, so it is going to experience a phase shift. Ray 1, I'm going to say its effective path length is equal to, well, I guess it's going to be 1/2 of the wavelength because it's a phase shift of 180 degrees when you hit off of a higher index of refraction and reflect. So then there's ray 2, and it's starting from the same place as ray 1. What are we going to bend, towards the normal or away from the normal going into the surface? I guess we'll bend towards the normal a little bit. So we bend like that a little bit, and then there'll be a reflection here. Now, there is another reflection that I'm not addressing, but there's a reflection off of here. There's some stuff that goes through, and there'll be some reflections forever in here probably, but that's all very complicated and sort of, let's call it second order effects. So ray 2 has a slightly different experience. It finds, well, it's going to go out parallel to ray 1 as well. So they will both reach your eye if you're very far away. These two parallel beams will meet at that point. And we need to know this distance here. We're going to define it as the thickness of the bubble at that location. And I guess the phase shift for ray 2 will be because it's traveled an additional distance compared to ray 1. So I'm just going to say the effective path length, and this is a real path length for ray 2, there we go, that's the effective path length for ray 1. The effective path length for ray 2 is twice the thickness. And I'm assuming that this ray is coming in normal to the surface and going out normal to the surface. I'm exaggerating this incoming angle because we've got to be able to see what's happening here. At this bounce here, though, is there a phase shift? Let's see, it's in a higher index of refraction and bouncing off of a lower. That's analogous to a loose end for a rope, so there's no phase shift here. No phase shift. And I should emphasize that right here, there was a 180-degree phase shift because of that, that tight end. Phase shift, not phase shirt, phase shift. Now, here's what we can do. We can do some really fun math. I want to remind you that, well, remember there are 3 things that comprise a wave. I guess a wave has wavelength and frequency and speed. Now, the speed of light is lower in here. Slow light. So what else is changing? If I write down this equation, I say that the speed of light in some substance is the frequency of light in that substance times the wavelength of light in that substance. If I go slower, does that mean my frequency is decreasing or my wavelength? That's a very important question, and you need to understand what waves mean in order to do this. A wave's frequency is determined by the source, and the speed is determined by the medium. So the wavelength is what responds to changes in speed or changes in frequency. If you're in a slower medium where n is greater than 1, then I guess you have to have, what, a longer wavelength? Whoa, a shorter wavelength, because the wave is trying to wave, but it's not going as far during that waving, so a wavelength is shorter in a higher index of refraction because the speed is smaller. Frequency stays the same because the frequency is set up by the source. So if this is red light coming in, then it will be red light going out. Was that hard to see me write red in green? Deal with it. Here's what I'm saying. I'm saying the wavelength in a medium is going to be the wavelength in a vacuum divided by n. Does that make sense? I guess, well, if we see, let's remind ourselves what n is. The index of refraction is the speed of light divided by the speed of light in that material. So it's always greater than 1 or equal to 1. If I'm dividing by a larger number, I'm going to get that the wavelength has been reduced. So then I can take these path lengths here and I can divide them. That'll be my fun thing. I'll divide these guys by the wavelength to try to figure out what the heck's going on. Because here we've got a wavelength. This is the effective wavelength shift of 1. That's the path length difference. And wait a second, this is the wavelength in a vacuum. It's very important to note that we have a wave out here and its wavelength is the wavelength of a vacuum. In here, the wavelength is different. So we've got a different sort of situation. Here's what I'm planning to do. I'm going to say L effective. I'm justified in doing this because, well, it's going to help me. So I'm just going to take this L effective 2 and I'm going to divide it by lambda n. Now, then I take this stuff here, which is just 2t, and I divide it by lambda n. Now I'm going to plug in what lambda n is. I'm taking this guy, and I'm going to plug it in right there. And I'm going to get, watch this, there's an n in the denominator of the denominator, so I put it up top, 2nt over lambda in a vacuum. Ooh, cool. So let's look at what the path length is. So, I'm going to say, so one final time, the path length difference divided by lambda in a vacuum is, well, that's going to be L effective 2 minus L effective 1 divided by lambda in a vacuum. And it's time for me to plug in some stuff. I'm going to get, wait a second, L effective 2, that's this stuff, divided by the lambda in a vacuum. Oh, it's already there. Okay, great. So I'm going to say that this is 2 times t, wait a second, 2 times n times t divided by lambda vacuum, and then I have to subtract a half. So here's the point. My point is, if this thing, this actual path length difference divided by lambda in a vacuum is an integer value, it means that we're going to have constructive interference. Do you remember the principal equation of interference? It says if the path length difference is some integer times the wavelength, then we have constructive, and if we have that thing equal to m plus a half, some half integer times the wavelength, then we have destructive. And so my point is, this is what delta L over lambda is. And so if we've got two, oh my gosh, look at that really complicated equation. My point is, if this equation is an integer, then we've got, wait a second, we've got constructive interference. So if it's a half integer, then we've got destructive interference. Let's simplify that a little bit. Look, if I say 2nt over lambda in a vacuum, look at that. Now that's a little bit simpler. If this is an integer, that means destructive, because see that half right there? I'm just taking out that half. And this is a half integer, then we've got ourselves constructive. So this is exactly the opposite of what you've studied before. Don't get confused. Here's the only thing that we've done. We got a half out here. So we took it out, and we were able to say if this is an integer, then we get destructive, and if it is a half integer, then we get constructive. Now, that doesn't help us at all. Wouldn't you agree that this helps us not one single bit? Unless we recognize that, yes, for a given thickness, you want to solve that for thickness? Let's just do it. We'll solve this equation for thickness. I'm saying if thickness is equal to, well, I guess it's lambda in a vacuum times some integer divided by 2 times the index of refraction. If the thickness is that big, then we've got destructive interference, and if the thickness is a little bit bigger, we've got constructive interference, and this depends on every wavelength. So some thicknesses allow certain colors to be reflected, and other frequencies allow other colors to be reflected, and that's why we've got different colors. But wait, why would there be different thicknesses in a bubble? Let's look at that for a moment. If I draw a bubble, you might draw it like that, but you might think that it's the same everywhere. Oh no, after a little while, if a bubble's floating around, it's like extra, it's got extra bubbly goo, you notice it's like down at the bottom right there, and it's probably actually going to be thinner up at the top. Why is that? Why is it so thin up at the top and so thick down at the bottom? Why are bubbles like that? Gravity. So gravity is providing the change in thickness that's allowing you to go from letting red be seen to letting blue be seen and going through the entire spectrum of the rainbow, in fact, several times over, which is why bubbles are beautiful. Yay. Ray number 1 is coming in, and the bubble material itself has a high index of refraction. So I'm just going to say n is greater than 1. Over here, we've got n is 1 because that's air on the outside of the bubble, and on the inside of the bubble, unless you're doing something interesting, n is also 1. So this is the surface of our bubble. If we zoom in on it, we can try to understand why these things happen. When there's a bubble, there's a very thin film of soap and glycerin, I guess. And then I could have this light ray that's coming in from who knows where. And here's this light ray, and ray number 1, well, it's coming in here. This is the incoming. About the bubbles is, whee, slurpy, slurpy. No, put some bubbles at the top, that's what I'm talking about. The cool thing about bubbles is they make awesome rainbow patterns. I don't know if you can see that on those bubbles. I'll try to get you a bigger one. But, here we go, wait for it. Bubbles, no bubbles. All right, just look at the rainbows in here. Ah, what a mess. Okay, see those beautiful rainbows? Now, we want to try to understand why those rainbow patterns are formed on bubbles. And if you're not seeing them on the video, go make your own bubbles. Have a little bit of fun. Sorry, this is such a mess. We'll see what we can do. Here's what I want to tell you. When a bubble, if you ever noticed, for instance, that the sky is blue, and that's beautiful, you might have also noticed that bubbles are pretty awesome. So I've got this jar full of bubbles right here. Unfortunately, we also drilled some holes through this. So you can make bubbles by, how can you make bubbles? I guess putting some glycerin together. Look at this bubble right here. I'll make some bubbles. The cool thing